Right, so this is lecture 2 of the logic course. So in case we want to title the lecture, what we're going to cover are mathematically logical theories, and one of the main means or mechanisms, if you like, that we have for getting a handle on theories, for being able to understand theories, which is Axiomatisations of theories. So the lecture is going to be called Theories and Axiomatizations. And the style for this lecture only, for the rest of the course, is going to be similar to last week's lecture, in that I'm going to intersperse technical, that is mathematical material, with some narrative. From next week on, the course will become essentially a purely mathematical course. Of course, there will be the narrative of the story we're telling throughout the course of how logic unfolds, but there's not going to be, but in this lecture, like last week, there's going to be much more informal, there's going to be a lot of informal material as well as the formal material. Maybe a difference between last week is that last week it was mainly informal for 2 parts of the lecture and then purely mathematical at the end. Today's lecture is going to be much more mixed up. So we're going to have a bit of technical material, then a bit of informal material, and then get back to the technical material and so on. So to make sure we're on the same page, let me just remind you of the crucial things you need to remember that we did last week. So we need the notion of signature. I mean, if you don't remember, hopefully the reminders you get during the lecture will be sufficient to help you remember. So we have a signature, which is denoted using a capital sigma, and the sigma gives us the signature gives us a vocabulary of function symbols, including constants and predicate symbols, and we use that vocabulary, use this to form syntactic constructions out of the vocabulary, and those are in particular terms T. So that's I tend to use S, T, and U for terms, the lowercase, and formulas, capital A, capital B, capital C. And we remember that the terms T, the idea of them is they represent elements of a mathematical structure, and the formulas A express properties of a mathematical structure. So what's a mathematical structure? Well, that depends on the signature. So also last week we had the notion of structure for a signature. So not T, that's a term. So structure for a signature is a kind of, we write using a curly letter, and it contains an underlying set together with interpretations of the predicate symbols and the function symbols. And the point of a structure is we can interpret the language in it. So we have the interpretation of a term in a structure. Term in a structure M. So this is the interpretation of a term in the structure is an element of the carrier set of M. So this has an underlying set and then some interpretation of the functions and predicate symbols. The underlying set, we use the same letter, but it's no longer curly. It's just a capital letter for the underlying set. For the interpretation of a term, maybe I wrote, well, so one thing one needs to do is to interpret a term. If it has 3 variables, we don't know how to interpret the term unless we have an interpretation of the 3 variables. That's given by an environment. So actually, the interpretation of a term T is relative to an environment rho. Maybe I did, or maybe I didn't last week. It doesn't really matter. Officially speaking, because it's the interpretation of the term in the structure curly m, officially speaking, we can put a subscript curly m there, but we don't want to be too fussy when we don't want to write lots of subscripts all the time, so I'll normally miss that out. And maybe one thing I didn't say last week is that if P has no variables in it, then this interpretation is independent of the environment row. It does not depend on the environment row. So if P has no variables, we simply have an element P interpreted in the structure M, which is an element of the set of the structure. And then the interpretation of a formula So apparently this question was asked in the exercise class last week. Why don't we interpret a formula in the same way as we interpret a term? In fact, we can do. This is not the notation I used last week, but we could perfectly well define the interpretation of a formula A in a structure M in an environment row that's assigning a value to three variables. And this will give us, if we're interpreting like this, this gives us a truth value, either true or false, because a formula expresses a property, depending on on what values we're assigning to the variables in the formula, that property might be true or false. So we could do that. And in fact, I did that, but I used a different notation for it. And the notation I used for it is this, the satisfaction relation. So for the same, so this means exactly the same thing. So I wrote it like this, that a formula A is satisfied by a structure by the structure M, given the interpretation of given the environment assigning the variables. So this, it's not, one could take two alternatives, or we could do it this way and this way. This expresses the same thing as that the value of this formula is true. So this relation holds if and only if interpreted this way, the value of the formula is true. In logic, this is the standard notation that one uses. So the traditional notation is to use the satisfaction relation, although sometimes people put this in a different place. So I believe Gregor in the exercise class put it as a subscript. Of course, it doesn't matter, as long as you stick to a notation and you're happy with it, it doesn't matter where you put things. So just to be consistent with the lecture notes, I'm going to carry on putting it here, to be consistent with his own previous practice, and also actually most textbooks in logic, Gregor will probably continue to put it there, but it doesn't matter. I hope you'll be able to navigate such differences. So let's put this in brackets. So this is kind of really one of the main things we introduced last week. So this is the satisfaction relation, which we can interpret as the interpretation of a formula in a structure. So this is the satisfaction relation. And to say one more thing about it, we had the notion of, so this works for an arbitrary formula. We have the notion of a sentence. So a sentence is a formula in which all the variables are bound by quantifiers, so there are no free variables. So if A is a sentence, then again the satisfaction relation is independent of the environment row. That's something you may prove in the exercise class, perhaps. So if A is a sentence, has no free variables, all variables are bound. So that means then we simply write we can simply say that A is satisfied in the structure or by the structure M. So A is, or another way of saying it is A is true in M. I'm still on last week, so I'm not going to always revise go through the previous week so thoroughly, but because it's the first lecture and, well, the second lecture now, but it was the first lecture last week and there are a lot of concepts I think it's worth doing today. So let me just move the So also last week we had lots of examples, and in particular, running examples were given by two interesting mathematical structures that are of clear mathematical interest, because mathematicians have spent centuries looking at what is true in them. So last week we considered two particular structures. This is still last week. Considered two particular structures of interest, two structures of interest. One is a structure based on the natural numbers, which, to give it a name with a curly letter, I'll call it curly n. That's the natural numbers with the usual interpretation of addition of the signature that we had with addition, multiplication, 0 and 1. And the other one was another structure with addition, multiplication, 0 and 1, but that's based on the real numbers of the carrier set. And as we saw last week, different sentences are true in these different structures, and the order relation is defined in a different way. So we'll call this one curly R. And so a lot of the informal discussion last week was based on these structures. So now I want to introduce the first new thing from the lecture today, going to the notion of a theory. And from a logical point of view, what's of interest in these structures is which properties are true of the structure. So we can say this, so a property, a formula with variables, its truth depends on the interpretation of the variables on the environment, but a sentence is either true or false. So it's quite a fundamental thing. Given a sentence, is it true or false? And so we simply collect together all the sentences as a set, all the true sentences as a set, and say that's an important piece of data about the structure. These are the sentences that are true, and we call this the theory of the structure. So all the facts that are true in the structure. So the theory of a structure M, in general, this is now an arbitrary structure, is defined to be the set A sentences, so A is a sentence over the signature of the structure, and A is true in the structure. So the theory of the natural numbers will contain sentences, so all the true sentences, so that will include sentences like the sentence that expresses there are infinitely many prime numbers. And the theory of the real numbers will also contain true sentences like the sentence that expresses that the strict order relation is dense, for example, between any two. You've got one number strictly less than another, then you can find another number in between those two numbers. That would be a true sentence here. Anyway, so we collect these things. So this is called the theory of the structure M. And just to remark, so as sort of motivation for some of the considerations that logic has, that I mentioned last week, an interesting question from a mathematical point of view is, if we're interested in a structure, how difficult is it to understand whether a sentence is true or not? And the ideal, the best situation one could hope for is that it's simple enough that we could write an algorithm to tell us if a sentence is true or not. And we saw, I already mentioned, there are two theorems that tell us that these two structures have very different properties in this regard. But the structure N, so this was already mentioned last week, but there's the theorem of Church and Turing, which is there is no algorithm for deciding if a sentence is true in N. And now with the notion of theory, we can formulate this in a very concise way, which is simply that we'll write theory of N, the structure natural numbers, is undecidable. And this is the mathematical theorem, precisely stated, although once again, there were questions last week about what is meant by undecidability. At the moment, you don't need to know this, and it's not a very major part of the course. This was more part of the computability theory course last semester. It's not really important for this course, but just to be, the point here is to get a picture of what sort of things are true, and what this means informally is there is no algorithm that tells us if an input sentence belongs to the theory or not. Belongs to the theory of natural numbers or not. So in other words, tells us, yes, it is true in the natural numbers, or no, it is false in the natural numbers. And the other theorem we had, that I mentioned last week, which contrasts with this for the real numbers, was Tarski's theorem, which is that, in contrast, the theory of the structure of the real numbers is decidable. So I'm not going to expand decidable in the same way, but well, you just change no to an. So there actually does exist an algorithm in this case that will tell us if the sentence is true or not. And while we're just reviewing this, just to say, mathematicians, so the correct notation for the theory of the natural numbers is theory of curly n, because it's the structure n. But when one does maths, one doesn't want to be totally pedantic all the time about notation. That's over fussy about being very strictly correct in every detail. And so people would normally write this simply as the theory of the natural numbers, like that. And again, you would normally write this the theory of the real numbers. It has to be understood, but when you're talking about this, you have to understand what the signature is. It's this one for the ring of real numbers, which is, of course, a field. And we're talking about the sentences that belong to that theory. Okay, so I need to find which way my notes go from here. So before carrying on, I just want to make an observation about this notion of a theory of a structure for an individual structure. So one thing we're going to do in this lecture is we're going to look at various ways of determining theories, logical theories. And this is the first example, the theory of an individual structure. We see that it's interesting because we have interesting examples, the theory of the natural numbers, the theory of the reals. And theories from a theory that's determined by an individual structure has a particular property, which we're going to see later, is not true in all theories. And this particular property is the following. So the theory of an individual structure is what's called complete. That's a complete theory. I'm clarifying here that complete in this case is an adjective that's qualifying theory. We're talking about a complete theory because we're going to see several different uses of the word completeness in this course. And so it's good to bear in mind which kind of complete we're talking about. So this is a complete theory, and the theory is complete. So this is a definition. So this is serving both as a definition and a statement of fact. The definition is the definition of complete theory. The statement of fact is that the theory of an individual structure is always complete. And so So what this means, so this is the statement of fact. The definition here is i.e. for any sentence A over the signature, either A belongs to the theory of the structure, or not A belongs to the theory of the structure. And this is a really honest use of either or in the English sense. When you say either or, people nowadays don't always insist on it, but historically either or was supposed to be an exclusive or. Only one of the two can hold. This is a case where it really is an exclusive or. One of these sentences is going to be in theory, but only one of them. Of course, there's not going to be any property that both it and its negation are true in a structure. And the reason for this is, well, simply we're literally talking about A belongs to the theory of M. The sentence A belongs to the theory of M if it is true in the structure M. And if it is not true in the structure M, well then not A is true by definition of not A. So it's basically trivial that this is the case if we're talking about the theory of an individual structure. So it's a trivial property at this stage, but nonetheless it's an important property because it's not going to be true. We're going to see other theories, and it's not going to be true that all theories are complete. Not all theories are theories of individual structures. Okay, so that's the notion of a complete theory. So when might a theory not be complete? Well, we'll get to that in a little bit, but we get to it by considering something a bit more general than the situation we've been looking at. So here we've been looking at theories of individual structures, but in mathematics, it's very often interesting and very often the subject of study is not the theory of an individual structure, but it's the theory of a collection of structures of interest. So let's go to the other board. And we're now going to get into a bit more of a narrative part. And I need to move the camera. So in mathematics, we're often interested in classes of structures where all the structures share the same signature for talking about them. This is the kind of situation that we can meaningfully say something about in logic, but it's something that really relates to mathematical practice. So in maths, we are often interested in classes of structures. Classes of structures of interest, we might say, but I'm not going to write that all down. Where you have an appropriate signature for describing the structures, and then you have a class of structures that depends on that signature. So examples. So I'm going to look at some different signatures and think about structures classes of structures that we might be interested in. So if we have the signature that contains one constant E, remember a constant is the same thing as a zero-arity function symbol, and one multiplication symbol dot, we could even call it M if we wanted to. So this is a constant, this is a binary function. Well, some classes of structure that naturally have this signature are group, which I'll define to be, so this is a collection of structures but is simply the collection of all groups, the class of all groups. So that would be one class of structures of interest where we can interpret this signature. The E is going to be interpreted as the identity element of the group, and dot is going to be interpreted as the multiplication of the group, of course. Or, yeah, related to that, we could have ab group, which is a smaller collection of all abelian groups, so groups in which multiplication is commutative. The class of all abelian groups. And I'm not going to write, I mean, there are lots of other interpretations of this signature too that are natural. So another mathematically natural one for those who know the concept would be the collection of all monoids, or the collection of all semi-groups with identity. So anyway, there are lots of other classes of structure that are naturally associated with this signature. All I want to illustrate here is that, you know, in mathematics, one considers essentially structures with signatures, and there are interesting collections of them. So let's consider some other examples. So if we had sigma to just be the signature that contains now a binary relation symbol, binary predicate symbol. I'm going to sometimes use the word relation symbol, sometimes predicate symbol. It means the same thing. A predicate is just a relation of whatever arity. So this is a binary predicate symbol. Well, of course, a natural collection of structures that would have this binary operation, you know, one tends, as I said last week, and I think would have been emphasized also in the exercise classes, it doesn't matter what you call things, because you can give function symbols and predicate symbols any notation you want, as long as you say how to interpret it in a structure. But when we're being mathematically sensible, we write things in sensible ways that we're going to understand. We're going to understand in a natural way. Of course, the very way I've written this suggests that a natural collection of structures is going to be structures with an order relation on them. So particularly natural class of structures for this is, I'm going to underline these collections of structures, the names of these collections of structures. So part ord is simply the class of partial orders. So that's sets with a partial order relation. Where if one's using this symbol here, by partial order, you would typically mean a partial order where the interpretation of this symbol is the strict order relation. So the order relation that's not reflexive, that's irreflexive. X is not strictly less than itself. So the class of sets with a partial order, or another, again, there's an interesting mathematical, well, there are many interesting mathematical subcollections of this, but one in particular that's considered a lot in mathematics is lin-ord, which would be the class of all linear orders, or another word for linear order is total order. So those orders in which every two elements, one is below the other or the other way around, or they're equal. As they satisfy what's called the trichotomy property in English. The class of linear orders. But you know, I'm not going to, at the moment, give all the definitions in detail, because this should just be suggestive of things you know to some degree in mathematics, and the point is to illustrate that there are classes of structures of interest in mathematics. And another signature would be, well, essentially the same signature. Again, this is a binary predicate symbol, but I've called it something different. I've called it E. And again, the point of that is to be suggestive that we're suggesting a particular interpretation, which now is the edge relation for a graph. So a natural collection of structures here would be what I'll call graph So there are many classes of graphs that people consider that kind of the most common notion of graph is the collection of all what I'm going to call, well, what people sometimes call simple graphs. So simple graphs are graphs in which the edge relation is symmetric, so they're not directed, and you have the property that you only consider edge relations between distinct vertices. So you don't have little loops from the vertex to itself. And let me just put ... because as you can imagine, there are lots of interesting signatures corresponding to lots of interesting mathematical classes of structures. The other point I want to make before going on from here is that notice that what we're doing here is somehow unifying two different kinds of collections of structures in logic. They all fall within the scope of logic. So one are structures that have constants and function symbols acting on them. And those kind of structures are the sorts of structures that one typically considers in algebra. And the other is we have structures that are sets with relations on them, so predicate symbols instead of functions and operations. And that's such things are called relational structures, and those include things like ordered structures and graphs and those kind of things, which are not normally considered part of algebra. Okay, but logic encompasses both kinds of structure. Right. So suppose we have a class of structure, and we're interested in class of structures, and we're interested in investigating it. Once again, just like when we look at an individual structure, we can ask, is a logical sentence over the signature, is it true? And now we've got a class of structures, so the natural thing to ask, is it true for all structures in the collection? So for example, one of the goals of group theory, I mean, group theory is a very deep subject, so this only captures one aspect of the goals of group theory, but one aspect of group theory is to understand truths about groups in the sense of finding theorems about groups, so finding sentences expressing properties of groups that are true for all groups. So it's very natural to have the notion of look at a sentence and see if or not it is true for all structures in the collection. To move the camera. So in general now, suppose we have a signature, and suppose M underlined, which to say it's a collection of things, is a class of sigma structures. A collection of sigma structures. The some fixed signature. So if you like, we might think about the signature for groups, and it's a collection of structures, some collection of structures for that signature. For example, it could be a collection of 4 groups, but the definition is very general here about just any collection of structures. So we're going to define the relation that says when a sentence holds for all structures in the collection. And again, we use the same satisfaction relation symbol here. And we simply define that to hold if and only if, well, that's what I said, for all structures in the collection of structures, A is true in the structure M. Okay, so here, because I'm not speaking about environments, A is a sentence. So notice I'm using the same symbol that we use for the satisfaction symbol. So in computer science terminology, this is now overloading of this relation. We're using it in two different ways. We're using it for an individual structure on the left, and now we're using it for a collection of structures on the left. Of course, I mean, they're very closely related, so it's not a big deal, this overloading, but I want to mention it at this point because it's a forewarning of what's to come, which is this symbol is going to be used in very, very many different ways in the course. And you have to pay attention to which version of the symbol is being used. It's traditional in logic to overload this symbol in many ways, so I'm going to stick with the notation that you'll find in textbooks, but I'm forewarning you about it now. So this is a little thing because it's obviously a natural generalization from an individual structure on the left to a collection of structures on the right. So now so basically we're saying A is expressing a true property of all structures in the class M. So the officially correct way of saying this, we say that is to say that A is valid, valid in M. So valid means true in all structures in a class. So truth is about being true in one structure, and valid is about being true through a class of structures. So that's the official way of saying it, but it would be very pedantic to stick to that all the time, and people don't have any problem, and I'm not going to have any problem with often saying, or often will say that A is true in M. So if we're talking about a property of groups, we might say, the fact that every element of a group has an inverse, that's a true property about groups. We don't want to be too fussy and say, well, actually it's valid rather than true because it's a property that's true across a class of structures rather than in an individual structure. So I'm just making this point because historically, in the development of logic, people were very, very pedantic in the first half of the 20th century, and gradually they've got less so. So these kind of distinctions are more or less emphasized depending on where you look in the literature. We're getting to the stage now that we can be a bit more informal about it, but it is important to be aware of the difference. It doesn't look like the board's completely in focus, so. And just like we defined the theory of an individual structure, we're going to define the theory of a class of structures. Maybe I can fit it back here and define the theory of a class of structures to be a set of sentences such that A is valid, to be pedantic and correct. A is valid across the class of structures M. So this is the theory of the class of structures M. So we could talk about the theory of partial orders, the theory of graphs, the theory of groups, the theory of abelian groups, and so on, meaning the true sentence, well, the sentences in that signature that are valid for all elements for all structures in the class. Right, so the next thing I want to do is now go to examples illustrating this, and but I think it's close enough to 9 o'clock that it's not a good time to do that. So let's go by the clock on the back wall. It's not available to people on Zoom, but anyway, we're going to take a 15-minute break from now. So it's 3 minutes to 9. So that means we start again at 12 minutes past 9 by the clock on the back wall. Okay, so we've got the notion of theory of a class of structures, and I want to illustrate it by telling you by looking at some properties in the theory of the class of groups and some properties true in the theory of the class of groups, and also some properties of the theory of the class of groups. So that's why I left the signature for groups and the definition of the collection of groups on the board. So we're going to have an example now. The theory, that's with a capital T, the theory of those sentences that are valid in the class in groups, in the class of all groups. So the following sentence is valid, or we might say, as I said, true in groups. So the following is, let's underline that to emphasize it is valid. So the kind of thing we can say in our signature about groups, something very simple, would be the following. So for all x, there exists a y such that x times y equals e, and y times x equals e. So you will notice this is a sentence that states that every element has an inverse, which is of course true in groups because it's the basic property of a group. The whole idea of a group is the idea that every element has an inverse in some sense. So that's valid, clearly, whereas the following is not valid. So in the collection of groups, so an obvious sentence that's not valid in groups, when one of the first things you learn about arbitrary groups is that there are groups in which the multiplication operation is not commutative. So we know this sentence, it's true in some groups, namely it's true in the abelian groups, but it's not true in all groups. And to be valid in groups, it would need to be true in all groups, so this is not valid in groups. But it is, of course, valid in the collection of abelian groups, because that's actually the definition of an abelian group. It's a group that satisfies this property. So that it is valid in class structures ab group. So the class of structures ab group, some sentences belong to its theory, are valid for abelian groups, but are not valid for groups. In fact, one can see that any sentence valid for all groups will always be valid for abelian groups, because abelian groups is a smaller collection of structures, and by the definition of the theory of the sentences that hold in all structures, it's obvious that if you make the collection of structures smaller, you retain all the existing sentences in the theory, but you may gain some more. You may gain some more validities as you make the class smaller. So it's clear that any sentence valid in groups will be valid also in abelian groups. But the converse doesn't hold, and this is the simplest and most natural example. But an interesting further property to observe is following, that neither of, and I forgot to move the camera, people on Zoom if any of you are still awake, please do shout if I forget to move the camera. Neither of the following two sentences below is valid in groups, valid in all groups. So the first one says there exists an X such that X is different from the identity element and X times X equals E. So in other words, there exists an element of order 2 in the group. So this is not valid because, yes, there do exist some groups that have an element of order 2, but not every group has an element of order 2. For example, the cyclic group on 3 elements has no element of order 2. But also, so this is not, neither of the sentences is valid. So it's not valid, but also this sentence is not valid. If we stick a negation on front, it's not true that there exists an X such that X is different from E and X times X equals E. So this says there is not an element of order 2. And of course, this is not valid either, because there are some groups that have an element of order 2. For example, the cyclic group on 2 elements is the simplest group with an element of order 2. Okay, so neither of these sentences is valid. So why did I give this example? What's the point I'm trying to make? Completeness. So the theory of groups is not complete. So whereas the theory of an individual structure is always complete, the theory of a collection of structures does not need to be complete. It can, sometimes it is complete. Sometimes you do have a collection of structures, but the theory is that they just all happen to satisfy exactly the same sentences. But in general, the theory of a collection of structures is not complete. Right, so just in the spirit of the kind of results we were looking at last week, I just want to mention something else before moving on. So, I mean, I hope you agree that if we could understand in a deep way the theory of groups, that would be the logical theory of groups. I mean, I've been looking at very simple properties we can express here, but one can express much more complicated properties about groups in this language. But if we could understand it in a nice way with, say, some algorithm to help us, then that would be a very useful thing for mathematics. So I want to mention 2 results from the 1950s related to this. These are results we're not going to cover in any way in the course, but as part of setting the context in these first 2 lectures. So the first one, I'll write the theorem. So this is from 1955. So it's by somebody called, well, I've got no idea how to pronounce it, but then one writes it in the English alphabet. That's the name, SZMIVLEW, from 1955. And this is the theory of the collection of abelian groups is decidable. And like the real numbers, what this means is, I'm not going to write it down again, but there exists an algorithm which we can write as a computer program that takes as input a sentence over the signature for groups. Yeah. And tells us, yes, if that is a valid sentence about a valid property and about abelian groups, and no, if it's not a valid property about abelian groups. Okay, so there's a nice complicated algorithm for doing this, but it's a rather striking result, particularly when it's contrasted against the following theorem due to Novikov, also from the same year, 1955. And this opened a question that, this was something that people had asked this question in the 1930s, and it had defied all attempts to prove it for a long time. It required some clever results, this proof. It's a really nice proof, but it's beyond the scope of the course, which is the theory of valid sentences across all groups is, however, undecidable. So there is no algorithm for deciding whether a property sentence in the signature over groups is true or valid across all groups. It's a very important result here, because from this it follows that many other things are undecidable too. So this was really a big achievement, both for the nice proof and also for the consequences that it's had. It's had quite an impact over the decades. One thing to mention is that actually it turns out even a very special case of this is undecidable. That even if we look at even if we restrict our inputs to sentences of a very simple form, it's still not possible to provide a computer program to decide them. So this is called, I'm not going to go into details, but it's called the word problem for groups. So even the word problem, which is a special case of this, even the word problem for groups is undecidable. And the word problem is, let's give ourselves some names for some elements of a group, of a group, assume some equalities between them. Does another expression of equalities between multiplications of these names, does that follow from the property from the equalities we've assumed? And that's a very special case of the sentences are easily expressible in our language, and even that problem itself is undecidable. Okay, so again, we've got the contra. So just rewinding a bit and getting a sort of high-level view of what we've just discussed. Well, I've introduced the notion of a theory of a collection of structures with motivating examples for that. And hopefully you can see, looking at collections of structures is something that's also of mathematical interest. And once again, we've got the same sort of contrasting situation that we had last week. Somehow the question, does there exist an algorithm to help us decide if a property is true or false, seems very, very sensitive to which class of structures we're looking at. For two quite similar looking things, groups and abelian groups, you get completely different answers. So questions like facts of life, like this undecidability result, raise the question, well, we don't have an algorithm that can tell us if a property of groups is a true property of groups or not. What tools do we have? Can logic provide us with any useful tool for establishing properties of the theory of groups? And not just for the theory of groups, but for the theory of a class of structures in general. What positive tools does logic provide? And logic does provide very important and significant tools for this question, based on two notions. The first is that of an axiomatization, and the second is the notion of a formal proof system. Okay, so I want to now, in the next part of the lecture, introduce you to these notions, the notion of an axiomatization, and at a high level, we'll do it in more detail later in the course. It's going to be one of the main things to look at in the course. But at a high level today, the notion of a formal proof system. So let's start with axiomatizations. And again, to move the camera, but I'll clear the board first. So the point of an axiomatization is we define a class of structures by simply axiomatizing, giving some axioms for the basic properties that the class of structures must satisfy. So an axiomatization, well, how do we define a set of properties? We simply give a set of sentences. So an axiomatization is a set S of sentences. I'm using capital S here for a set of sentences. And any set over a given signature, but it goes without saying, whenever we talk about something like a set of sentences, we mean over a given signature that we know what it is. So if we've got a set of sentences automatically defines a class of structures, namely all those structures that satisfy these sentences. That's the point of the sentences of the axioms. We want to say we are interested in structures satisfying these properties. So an axiomatization or any set of sentences defines a collection of structures collection, which I'm going to call, so again, I'm going to underline it to say a sort of potentially large collection of structures called mod of S, because we're going to call these structures the models of S. Okay, so it's a collection of structures by what the models of S. Define that to be simply all those structures for our signature, such that for all sentences A in S, so all those structures that satisfy every sentence A in S. And normally we abbreviate this thing on the right by that. So now we're further overloading the satisfaction relation, because now on the left-hand side, we don't have structures or a structure or a collection of structures at all. We've now got a collection of sentences. And this is actually now called the entailment relation rather than the satisfaction relation. And I think I'm going to talk about that a little bit later. So I won't go into I think it's good to leave that a little bit later, but just to say we're going to use this notation. So once again, the warning, whenever you see this symbol, pay attention to what's on the left-hand side. Is it a structure? Is it a set of structure, a collection of structures? So, I mean, a set of structures would be okay, but in general, it might be a large collection, like a class of structures. Or is it, as in this case, a set of sentences? And in which case it means this. And as I said, these are called, the elements, the structures belonging to this collection are called the models of S.
How do you recognize which structure we're talking about with this notation? You can,
sorry, what do you mean which structure?
now we have S and implies something. That's an abbreviation for M. A is true in M.
So I'm saying this notation says, so we're looking at the set of all structures M,
Yeah.
such that M satisfies every sentence A in the set S of sentences.
Yeah.
So I'm struggling to see what's not clear.
She doesn't mention M. The upper should be M,
Yeah.
and then S. So S satisfying M.
Ah, right. Yes, you're right. Ah, thank you. Hang on. So this isn't actually in my notes, this part. So let me think about it. Yeah, so this is wrong. Good, thank you very much. Yeah. So we will introduce the entailment relation. But the entailment relation talks about, quantifies actually over structures. And here we've got a particular structure. So thank you. I don't know what got into me. That was it's amazing how you sort of get into a kind of autopilot sometimes, and actually it doesn't make sense. So good. Later on, we shall overload the satisfaction relation again, and it will become the entailment relation, and it will at that point have a correct definition. And it's very sensible that I didn't try to do that. Oh no, actually, so I've got something else in my notes, right? So actually, we do have an abbreviation for this, but it's not to do with entailment relations. Right, so we sometimes use that notation. Right. So every sentence on the right is true in the structure M. Okay. Anyway, so this is now version 3 of this symbol, and version 4, as you know, now is coming later. And I apologise for that mistake. And thank you very much for picking it up. And sorry for my slowness in seeing that there was something wrong. So as you may already appreciate, because it's actually not a deep point, because this is the access we have to these classes of structures. The main classes of structures I've talked about so far: groups, abelian groups. What else did we have? All the various classes of order relations and graphs. These are all not only naturally given by axiomatizations, but that is the very way we define them in the first place. So groups, the point of how do we define a group? We say these are the axioms for a group. These are the basic properties of a group. So examples of axiomatizations. So an axiomatization of groups, collection of all groups. Well, we've seen this before, but just to do it formally in our language. Well, what is a group? It's well, we have the signature, it has the identity, it has the multiplication. We want the axiom that says the identity is an identity for the multiplication. So for all x, so for all elements of the group, e times x equals x, and x times e equals x. We want the axiom saying that multiplication is associative. So for all x, y, z, which strictly means for all x, for all y, for all z. If we have x times y times z, then that's the same as x times z. So of course, you know the axioms for a group, but just to show that they do naturally, one can naturally write them in our language. The last one, the existence of an inverse, we've already had. It's a bit more interesting because it involves an existential quantification. So if one wants to treat a group as an algebra, you might sometimes put an inverse operation in. We don't need an inverse operation because we can simply say there exists, every element has an inverse, so there exists an element that acts as the inverse. And in fact, then you can prove that it follows from these axioms that that inverse is uniquely determined by the element it's an inverse for. Anyway, let's not bother going into such things ourselves. So these are the axioms for a group. As hopefully you all know, it is a collection of sentences. It's a collection of exactly 3 sentences. Often when we're writing them out, when you write out axioms, the axioms are intended to be sentences, but you don't bother to put the universal, oh, sorry, not this case. Here the existential quantifier is important, but you often don't write explicitly the universal quantification. You leave it implicit, but really an axiomatization is a collection of sentences, so the universal quantifier is really there. So if S is the set above, is the axiomatization above, then hopefully you can see that mod of S, collection of models of S, is exactly a collection of all groups. Okay. And if we added another axiom saying that multiplication was commutative, then we would get the collection of abelian groups. Right. So in the same way, we can give axioms for the collection of partial orders and for the collection of linear orders and for the collection of simple graphs. I don't want to be too thorough about this, but let's just do partial orders. Are axiomatized by, well, so I was thinking of partial orders. You choose when you define as partial order if you have the strict order relation or the non-strict one, the less than equals relation. If you have the non-strict one, then you have a corresponding strict one and vice versa. It's easy to go between the two. I'm going to have, for this axiomatization, the strict order relation is basic. So of course, the strict order relation is transitive. But because we've got implication in the language, that's easily expressible like this. Again, it's a sentence, so it's universally if the quantifiers we haven't put in, all the variables are universally quantified. That's how that one would normally write it like this, and one just understands that it's implicitly universally quantified. And lastly, it's not the case that X is less than itself. And that's all the axioms you need for strict partial order. So in particular, it follows from that for any X and Y, it's not the case that X is less than Y and Y is less than X. So linear order, you add a trichotomy that X is less than Y or X equals Y or Y is less than X. Let's not bother to write that down. So just to say simple graphs, to emphasize what I meant. So they're axiomatized by, well, the edge relation is symmetric. And that other property I said that it's not the case that there's a loop from any vertex from a vertex to itself. Okay, so we've looked at collections of structures, and we've seen that these structures are naturally defined as models of a simple axiomatization, and that's indeed how they are normally defined in mathematics, these collections of structures.
Can I just ask something?
Yes, please do.
Is there any difference between saying that a class of structures forms a variety and that it has an axiomatization?
Right, that's a very good question. So in algebra, you have the notion of a class of structures forming a variety, and that makes sense for a class of structures that you have constants and function symbols on it, And forming a variety means you have an equational axiomatization. So it means you've got a collection of equations involving operations. So the operations like the multiplication operation in this case, but more generally operations. And you just got, yeah, so you just got it. So then you consider those structures that satisfy those equations. But here we've got additional power because we've got the whole power of first order logic, including the existential quantifier. So in the case of a group forms a variety. That this axiomatization is not a simple equational axiomatization. The groups form a variety because it turns out that from these axioms the inverse is unique. So if you want to present them explicitly as a variety, you can add the inverse as an operation, and then you have a purely equational axiomatization. You don't have, there's no existential quantifier involved. But the existential quantifier allows us to define classes of algebraic structures that are not just equationally axiomatizable. So fields would be one example of that. So fields are not a variety because the multiplicative inverse is not a total operation with a pure equation, but the multiplicative inverse has the condition on it that it's only applicable to elements that are different from zero. So fields can easily be axiomatized here, but also one can axiomatize much more complicated things. So we include varieties, but our collections of models are actually not just varieties, but much richer classes of structures. So in some sense richer. Of course, varieties have a lot of advantages to them because if you've got a variety, the variety is defined in a simple way using equational axiomatizations, and that gives you lots of properties of the collection of structures that you don't have, that are only there because of the way that you're axiomatizing them to form a variety. So things like being able to quotient bicongruence, for example, which you can do with within a variety, but it's not going to be possible for any structure if you've got sort of more general axioms applying to it. So very good question. I hope that was a sufficiently thorough answer. Good. So we can axiomatize varieties. We can axiomatize also other richer classes of algebraic structure, and also classes of relational structures like orders and groups. And one of the nice things about having axioms and axiomatization is that we turn the question, is a sentence valid in the class of structures? Rather than thinking about the structures ourselves, we can turn that into a question, does the sentence follow from the axioms? And that's an equivalent, because the collection of structures is axiomatized, that is an equivalent question. So the point, really the main advantage of having axioms is we can then look at, we're then interested in, we've axiomatized some notion that we're interested in, and we can ask the question, what are the consequences of the axioms? Which is a whole essential approach to mathematics. This is what this is the approach to mathematics pioneered by the ancient Greeks. Have some axioms and then the axiomatic method, and then find out what the consequences of the axioms are. So logic provides us with the mathematical tool for understanding what this really means. And that is now, so now we get to the concept that I misdefined before, but very important concept, the notion of an entailment relation. So the notion of logical entailment formalizes the concept of a sentence A following as a logical consequence from the logical consequence of would be the better connective of a set of sentences S. And this is important because the idea of axiomatizations in mathematics, going back to the Greeks, is our axioms are the basic properties. And once we've got the basic properties, we then want to see just, we try to axiomatize all the basic properties we need so that everything else follows from them by logic. So this entailment is written as I wrote it before. Now we say A is a logical consequence of S, or S entails A. And the correct definition of this now, so we had the incorrect definition before, but the correct definition is that for all structures M, for the signature that we're assuming all the sentences are over a signature, for all structures M, if M satisfies all the sentences in S, using the notation I introduced before here, then M also satisfies A. So in other words, A is true in all structures that satisfy all the axioms. Okay? So in other words, another way of writing that is for all M in the models of S, saying exactly the same thing. So A is true in every model of S. Okay, so two different definitions there, but it's the same. They're trivially different. Let's just box the main definition. Okay, so now we do have our fourth version of this symbol here, where we now got the set of sentences on the left and the sentence on the right, defined in terms of the third version and the first version of the symbol.
Can you also just say that A is true in modulo S, so mod S the relation A? Since
Yes, indeed. So it's exactly the same as we also had the second version of the symbol where we have a collection of structures on the end. Very good. So this is the same thing as this by definition, and just by again unfolding the definition, this is exactly the same as saying that S, sorry, that wrong way around. That A is true, A is valid across the models of S. So thank you very much. Okay, so this and this are both replacements for the right-hand side of the definition here, but they're all trivially equivalent to each other from the definitions. Okay, and what's in the bottom, if you like, is the main definition. So we say, I don't have space to write it, but I said it. I think it is important to write the terminology, so have it in your notes. So the terminology, as I said, is S entails A, or A is a logical consequence of S. So I'll write it on this board. Terminology. S entails A, or A is a logical consequence of S. There's a very important special case here, and that special case is when the collection of axioms is empty. And so if the collection of axioms is empty, you're simply saying A is true in all structures for the signature. So in other words, A is true by virtue of logic alone. Well, A is true in all structures. So an important special case we simply write that. So now, so here, we don't have anything on the left here. So when we don't have anything on the left, we mean we're interpreting this as the entailment relation, and we've got the empty set of sentences on the left. So this means meaning the empty set of sentences entails, so this is of sentences, entails A, or in other words, for all structures, without any assumptions, A is true in the structure. So A is true in all structures, therefore it's true by virtue of logic alone. And there is important terminology for this. We say A is logically valid. And I'll put the logically in brackets because we often abbreviate that to valid. Or alternatively, A is a tautology, which, as you know, I hope, I think there's a similar word in Slovene, is tautology means exactly what I said, true by virtue of logic alone. Okay. Just trying to think when the best place to. Okay, so what I'm going to do here, it's nearly time for the break. So rather than going to the next major development, I think I'll save that for after the break. I just put one further definition associated with entailment, and this is to do with the notion of theory. So we have seen so we've got various ways of defining theories. We've got the theory of an individual structure, which we've already seen. And as we already saw, that's a complete theory. So for every sentence, either it or its negation belongs to the theory. The theory of an individual structure. We have a theory of a collection of structures. Now, another natural thing to have is the theory of an axiomatization, or the theory of a collection of sentences. So this is defined to be the set of all those sentences A that are entailed by the set of sentences S. So this is the theory of an axiomatization, if you like, an axiomatization. And all these theories share a common property, which is the abstract definition of a theory. So a theory, they're all sets of sentences. They need not all be complete, but there is a mathematical property that they all enjoy. So these are all theories. They're called theories, but in the following, according to the following definition, which I guess I need to clear another board for. So these are all theories. Sorry, I haven't moved the camera. So these are all theories according to a set of sentences is a theory if it is closed under logical consequence. So if a set of sentences P is a theory if whenever T entails A, then A is a sentence in T. So a set of sentences is called a theory if it contains every sentence that it entails, right? This is for all sentences A. So the point of a theory is we collect together all the logical consequences of something. And because it's closed under logical consequence, it enjoys this property. And it turns out that all these ways of defining theories we've defined, those all give theories that satisfy this property. I'm not going to prove that. It's a good exercise to prove this for yourself. So it's a very simple consequence of the definitions. It's just a question of sort of working through the logic of the definitions. And maybe one other thing I want to say is that something else that's going to be important later is we define the models of a theory, define the theory of a class of models, but we can go in the other direction and define the class of models of a theory to be the collection of all structures such that, well, in fact, the models of a set of sentences to be the collection of all structures. Oh, we did define this already, didn't we? Yes, good. Well, in that case, well, so I make it, well, the clock on the back will make it 1 minute to 10, but we'll start again at 10:15. So we'll have a 16-minute break. Okay, so I'm pausing the recording. Right, so so actually today's lecture is going to be almost the opposite of last week, and that now for the third hour it's going to be, rather than technical, we've already done a lot of technical definitions today. So this is the last part of the introductory 2 lectures of the course, that's going to be narrative now. So and it's essentially narrative because what I'm going to talk about, we're going to come back to it in future lectures, but it requires a lot of development. Each of the points requires a substantial amount of development, but because it's important to the subject itself, I think it is really worthwhile understanding now the overall picture of what we're going to do. And what I want to focus on is an aspect of logic that is in some ways maybe the most important part of logic, which is something that I haven't mentioned at all so far in the previous 5 hours of lectures. And that's the notion of reasoning, logical reasoning. I mean, you know something about the history of logic. It goes back to at least to Greek philosophers, and for Greek philosophers, reasoning was really one of the be-all and end-all of logic. Aristotle introduced, or at least discussed, the notion of syllogism, where a syllogism is a correct inference principle that allows you to infer new truths on the basis of established truths by applying the rules of logic. And the most famous example of this is the kind of inference of the form that all men, meaning humans in this case, are mortal. Socrates, the famous philosopher, is a man, or was anyway. Therefore, logical inference, Socrates is mortal, which he definitely was because he died a long time ago. And in fact, as you may know, Socrates' death is very well documented. Anyway, the point is there are reasoning principles there. That's a particular example of a reasoning principle where we are correctly reasoning purely on the basis of logic to, as I said, to uncover a new truth based on truths we have already established. So a major contribution, but I'm going to write exactly what's in the notes because many could argue that this is the major contribution of logic. Contribution of logic is that it provides a collection of formal reasoning principles, and these are captured by what are called formal rules for reasoning. Now, these rules for reasoning are a little bit complicated. This inference about all men are mortal, Socrates is a man, therefore Socrates is mortal. That will be an easy example of a proof using these rules for reasoning, but there are the rules for reasoning are in general a little bit complicated. It's going to require a whole lecture to look properly at the rules for reasoning. But the amazing thing is that one can provide them a tool and that they are as well behaved mathematically as they are. So in particular, what we're going to introduce in this course is we introduce the notion of later in the course, we're going to introduce a formal proof system and formal proof systems. I keep on using the word formal. Formal here means everything is according to precise mathematical rules. If formal, you're being very, very careful and precise. We're going to, that allows us to give, so this is a proof system that allows us to give a formal proof or formal proofs. Keep on saying the same thing over and over again. So formal proofs that a sentence A is a logical consequence of a set of axioms S. So as I say, the actual rules themselves, that's a subject for a future lecture. But what it means mathematically is, so in a later lecture, we shall give, later in the course, a precise mathematical definition of a relation between sets of sentences and a sentence. So this relation is going to be written like this. So notice we're using a similar kind of symbol. This symbol is called the turnstile. And what this means, so meaning, what this means is there is a proof of the sentence A using only axioms from the set of axioms S, meaning there is a formal proof, not just a proof, but a formal proof. That's a proof, a precise sequence of inferences following the precise rules of inference. There is a formal proof of the sentence A showing that it follows from axioms contained in the set S. You don't need to use all the axioms in the set S, but you have to make sure that any axioms you use come from the set S. Contained in set S. And moreover, these formal proofs satisfy two very important properties. A formal proof is a finite structure. Depending on what notion of proof, we're going to consider two different kinds of ways of giving formal proofs. But according to one of them, a formal proof is just a finite sequence of formulas. So e.g., a sequence of formulas. That's one important property. And the second one is that there's an algorithm, there's a computer program, even an efficient one, which can read the proof and check that we haven't made any mistakes in our reasoning. Okay, so you know, one of the thorny problems for mathematicians is mathematicians like to prove theorems, but you know, one's being a bit informal at some level, and it does happen that mathematicians make mistakes, and sometimes it's discovered, and sometimes not for a long time it's discovered. But if you use a formal proof, then you can't make a mistake. Well, you can get a computer to check for you that you didn't make a mistake. And nowadays you can get a computer to help you make the proof as well. So this is a big growth area at the moment, and people in this department like Andre Bauer are working very actively in this area. But the important thing theoretically, well, and practically, that allows this technology to be developed is there is an efficient algorithm that can be actually implemented in software and is implemented in now software that's becoming practical. There is an efficient algorithm that checks formal proofs for correctness. So how does this notion of formal proof relate to what we've been discussing so far in the course? And for this, there are two cornerstone results that relate to the notion of formal proof to what we've already talked about today. So let me move the camera. There are two fundamental results. So one is called the soundness theorem. This is actually a relatively straightforward theorem to prove. The soundness theorem says if we have a formal proof that A follows from S, then A is a logical consequence of S. The whole point of formal proofs is to derive logical consequences from your axioms. And this result is saying we're doing the right thing with the formal proof. Our formal proof, our proof system, the rules of our proof system are correct. They don't allow us to derive things they only allow us to derive logical consequences from our axioms. So let's put that in the box, and that's actually relatively easy to prove. So this one has the definitions in place. So i.e., the rules of the formal proof system is correct. In the sense that this was the whole idea that we wanted it to derive logical consequence. But the other important result is that the converse of this, so this is of course for all sets of sentences S and for all sentences, individual sentences A. But the other cornerstone result is the converse to this theorem. Sorry, Matteo, you're raising your hands.
Correct, meaning without logical.
Correct means this. So that's the point writing it. I just mean, yeah, I mean, if this weren't true, you would be able to derive something that was not a logical consequence. And if you were doing that using your rules, there must be some rule that has been incorrectly formulated in the sense, because it would allow us to prove something, a purported consequence that is not an actual consequence. So the converse is called the completeness theorem. And it's just the converse. So if A is if a sentence A is a logical consequence of a set of sentences S, then we can find a formal proof of that fact. A proof that we can write down and the computer can check for us to tell us that it is an actual proof, so that we haven't made a mistake. All right, I just want a bit more space there. Does anyone know which mathematician proved the completeness theorem? I mean, you haven't taken the course yet, but somebody might happen to know. It was Gödel, yeah. So if you're saying the right thing. So this is Gödel's completeness theorem. So as you probably know, Gödel is famous for his incompleteness theorem. But still, this is one of the major results. This is not such a substantial result of his completeness theorem, but this is one of the major results of logic. It's also due to Gödel. It's the completeness theorem. So it's kind of almost a bit schizophrenic in a sense that Gödel, two of his famous, most brilliant results are a completeness theorem and an incompleteness theorem. It's almost paradoxical. It seems paradoxical. Of course, the completeness and the incompleteness are in two different senses. In fact, we're going to see a statement of Gödel's incompleteness theorem in a moment. So the completeness theorem here is complete in this sense. Complete in the sense of, so complete here means complete here means the rules are, I'm going to use the word complete again because I can't think of a better English word to use for it, but complete for deriving all logical consequences. So it's complete in the sense, if this weren't the case, then we would find some logical consequence we can't derive, try to analyze the reason for that, and add a new rule for that. So
there's sufficient.
Sufficient would be a good, yes. Okay. Very good, thank you. Sufficient for deriving all logical consequences. But the complete is appropriate for the reason I just said, which is if this were not the case, we would be tempted to add, as long as we've got soundness, we would be tempted to add some rules that we've forgotten and to try to make this the case. It's actually quite astonishing that we can achieve this. So a consequence of this is, if we look at the we go back to the theory of groups. So the theory of groups is undecidable. Is undecidable. I've already said that. That was Novikov's result. So if we've got a sentence about groups we want to establish it's true or false, we can't subject it to an algorithm. We can't just input it to a computer and say, tell me if it's valid in groups or not. But we still have a positive thing we can do. We can try to prove it from the axioms. And if it's true, if it's valid for groups, then by the completeness theorem, there will be some proof. Okay, so, however, if A is valid as a sentence, is valid in groups, so in other words, if A is a sentence in the theory of groups, by the completeness theorem, we can prove it. We can find a formal proof that will prove the theorem. It is possible we can find a formal proof that will prove A from the axioms of groups. From the axioms for groups. So we're kind of in, I mean, what I would say a happy situation about groups. If we've got something we want to prove, if it's actually true, if it's a valid sentence about groups, we will be able to prove it. I must say, not all the theorems of group theory, the interesting theorems, not all of them can be formulated as sentences in our logical language. This doesn't cover the whole of group theory. But for anything that can be formulated as a sentence in our logical language, if it's valid about groups, then there will be some proof of it. But nonetheless, one still needs an intelligent mathematician, because there isn't an algorithm that will tell us if there's a proof or not. One still needs an intelligent mathematician. So we're kind of in the paradise of mathematicians, if you like. You need a mathematician to be insightful to find the right proof. But once the mathematician has found the right proof, the computer, I mean, if it's true, there will be a proof as long as the mathematician's clever enough to find it. And then a computer can check that the proof is correct. So just to make sure that the mathematician hasn't made a mistake. So group theory is an absolute paradise in this sense. But it would be nice if the rest of mathematics were like this. So here a nice word for this, I think, a nice English word is we've mitigated, that's reduced the damage of the undecidability of the theory of groups. We have to live with the undecidability of the theory of groups, but there's a nice and satisfying picture about what we can do in group theory. So that's dealt with one of our theories that we couldn't solve by computer automatically, group theory, we've got a nice solution to. So let's now go back to the other theory, number theory, that we couldn't, the other theory that was undecidable, that we did not have a computer algorithm that would tell us if a sentence is in the theory or not. So let's see if Axiomatization can help with number theory. There is. So actually, before moving on to that board, let me put this down. So let me put this down as a slogan: Axiomatizations and proof systems help with group theory. That's the sort of summary of the of the conclusion there. So let's go back to number theory. Right, I need to move the. So can an axiomatization help with number theory? And we can begin with some good news. There is a natural and useful axiomatization for number theory in practice. By number theory in practice, that's for deriving the truths of the natural numbers that one tends to encounter in the real world. Number theory in practice. Does anyone know what this is called? Yes, very good. So this is called piano arithmetic. The piano, let's call it piano arithmetic. So the piano axioms arithmetic. The piano axioms for the natural numbers. What do we mean by it's useful for number theory in practice? So pretty much all known theorems of number theory that can be formulated in the language of number theory are known to be provable in piano arithmetic. So PA works well in practice. For example, PA proves, and I'm not going to write down all the sentences using logical formulas again. PA proves there exist infinitely many primes. That's a very simple property, but if you couldn't prove this, then it wouldn't be very good. So PA also proves, piano arithmetic also proves the prime number theorem. Very famous theorem in 19th century mathematics, the theorem that establishes that the density of prime numbers in the natural numbers has a logarithmic decay to it. Now this is really non-trivial. The prime number theorem was initially proved in the 19th century using complex analysis and using the Riemann zeta function. In the 1950s, an alternative proof was found by the Hungarian Erdős and also Norwegian mathematician, number theorist who won the Fields Medal. Anyway, it doesn't matter, but anyway, this was considered a very significant achievement in the 1950s, and one of the two people involved with this won the Fields Medal, the main mathematical prize, for work including this, but Selberg, I think his name is, but for work including this, but not only this. So anyway, piano arithmetic is enough of an axiomatization to prove difficult results. That's to say, it is believed that piano arithmetic proves. So I'm saying proves here. This is one way of reading this. What I mean is that, this means there is a proof of this sentence from the piano axioms. So this FLT here means Fermat's last theorem. So Fermat's last theorem, as you will know, is was proved in the 1990s by Andrew Wiles, but the proof uses a lot of complicated higher level algebra. And I mean, anyway, I don't know how the proof works. It's a very substantial proof, but people in the know believe that actually the proof can be carried out in piano arithmetic. But this is by no means trivial, and it's not actually been done. But somehow people believe that, you know, somehow the abstract mathematical methods used in the proof of in the actual proof of Fermat's theorem can be eliminated in favor of the elementary methods. I mean, basically, piano arithmetic gives you proof by induction. So you have to prove everything by induction. But people believe that Fermat's last theorem, but this is not checked there. So piano arithmetic is people believe practically a good axiomatization of number theory. So that's the good news. But the bad news is the other main theorem by Gödel in this course. So Gödel's incompleteness theorem. I mean, I say bad news, but whether one interprets it as good or bad is, you know, open, is subjective. And in a sense, you know, I don't really believe it's bad news. I mean, it's a fact of the world, and it actually makes the world a much more interesting place because of Gödel's incompleteness theorem that I'm now going to give you a little introduction to is a really interesting result. But it does mean that the situation for number theory is very different from that for group theory. I mean, you know, group theory, we're dealing with a collection of axiomatized structures to begin with. Number theory, we're dealing with a particular structure, just one structure, and we want to get truth in that structure. So the bad news, that's in my notes, but I don't want to write it, bad news. So it's believed, so let's put it like this. PA seems complete enough for the natural mathematical statements for the natural statements of number theory. But it has limitations. Limitations are made clear by, then we're going to have Gödel's first incompleteness theorem, which already, although we don't know what the notion of proof system is, but nonetheless, I can, basically, we don't know what piano arithmetic is, but nonetheless, we can more or less understand the statement given those two modulo those two gaps in our knowledge. So we've got Gödel's first incompleteness theorem. The goal of this course, the main goal, is to do enough logic to get up to Gödel's first, and then beyond that to it's Gödel's first incompleteness theorem, because actually he had two incompleteness theorems, and the even more interesting one is the second incompleteness theorem. But that's I'll just say that very briefly what that is today, because it requires some more difficult concepts. The Gödel's first incompleteness theorem is that one can exhibit, meaning you can actually come up with an explicit thing, and that actually, let's say one can find an explicit sentence A. I don't know why I call it A here, let's call it G, which is what I'm going to call it later in the course. An explicit sentence G in the language of arithmetic. The language of arithmetic is the one that we had last week, which is just the signature with 0, plus, times, and 1. interpreted in, that we think of interpreted in the natural numbers. So such that three properties hold. So firstly, so this should be really curly N, but I'm already going to the more informal style that I mentioned earlier. This is G is a true property of the natural numbers. So let's write that out. So G is a true property of the natural numbers. But secondly, we can actually prove that it's impossible to prove it from piano arithmetic. It does not follow from the piano arithmetic axioms. So G is not provable from the PA axioms. And thirdly, also the negation of G is not provable from the PA axioms. Now, if the negation of G were provable, that would be alarming because G is a true property of the natural numbers. If the negation of G were provable, then that would mean the piano axioms can prove something false about the natural numbers. And then we'd be left in a very perplexing situation because we'd be struggling to understand how we can prove something false from the piano axioms which look so true, because they are true. But anyway, just to reassure you, also the negation is not provable. So not G is not provable. So why is it called an incompleteness theorem? So now it's incomplete in the first sense. The theory of piano arithmetic is incomplete as a theory. There is a sentence such that neither it nor its negation belongs to the theory. So here, incomplete means theory of piano arithmetic is an incomplete theory, as defined earlier. Okay, so this is a problem in that piano axioms, we can see they're not sufficient for proving all truths of arithmetic. And we found actually a sentence that's true. So we could just add that sentence as an axiom for piano arithmetic and then hope that we've fixed the problem. But Gödel's first incompleteness theorem is actually much more pervasive and unavoidable than that. And the more full statement of it says that for any set of axioms for the natural numbers that we can effectively write down, so any set of axioms that we're able to write down will suffer from exactly the same incompleteness phenomenon. So no matter how many new true properties we try to add, we'll always then, once we've added them, we'll be able to find and explicitly find a new sentence that's still true, but not provable. Okay, so we can't fix the problem. It's an intrinsic problem of natural numbers. So in contrast to in group theory, one just has to be clever enough to come up with the proof. In number theory, we don't even have, and we cannot ever have, a complete set of axioms. So there's even more room for creativity for the mathematician. The mathematician doesn't just need to come up with the proof, but potentially to realize have new insights into new things that allow us to establish truth. So that's that is Gödel's first incompleteness theorem. His second incompleteness theorem is then about actually one sentence that we cannot prove is that piano arithmetic cannot prove that it itself is consistent. And that requires an introduction to that requires a little bit more sort of context. So I'm going to postpone that to the end of the course. Just want to have a quick look at my notes to see there's anything I've missed out. I don't think so. So that's everything for today. We're finishing slightly early. I'm going to stop the recording.